In this lecture, we complete our discussion of multiple continuous random variables. In the first half, we talk about the conditional distribution of one random variable given the value of another. We will see that the mechanics are essentially the same as in the discrete case. Here, we will actually face some subtle issues because we will be conditioning on an event that has zero probability. Nevertheless, all formulas will still have the form that one should expect, and in particular, we will see natural versions of the total probability and total expectation theorems. We will also define independence of continuous random variables, a concept that has the same intuitive content as in the discrete case. That is, when we have independent random variables, the values of some of them do not cause any revision of our beliefs about the remaining ones. Then, in the second half of the lecture, we will focus on the Bayes rule. This will be the methodological foundation for when, later in this course, we dive into the subject of inference. The Bayes rule allows us to revise our beliefs about a random variable, that is, replace an original probability distribution by a conditional one after we observe the value of some other random variable. Depending on whether the random variables involved are discrete or continuous, we will get 4 different versions of the Bayes rule. They all have the same form, with small differences, and we will see how to apply them through some examples.
By now, we have introduced all sorts of PMFs for the discrete case: the joint PMF, the conditional PMF given an event, and the conditional PMF of one random variable given another. And we're moving along with a program of defining analogous concepts for the continuous case. We have already discussed the joint PDF and the conditional PDF given an event. The next item in our menu is to define a conditional PDF of one random variable given another random variable. We proceed by first looking at the definition for the discrete case. A typical entry of the conditional PMF is just a conditional probability, but in different notation. And using the definition of conditional probabilities, this is equal to the ratio of the joint divided by the probability of the conditioning event. Unfortunately, in the continuous case, a definition of this form would be problematic because the event that y takes on a specific value is an event that has zero probability, and we know that we cannot condition on a zero probability event. However, we can take this expression as a guide on how to define a conditional PDF in the continuous case. And this is the definition, which just mimics the formula that we have up here. Notice that this conditional PDF defined this way is well defined as long as the denominator is a positive quantity. Let us now try to make sense of this definition. Let us first recall the interpretation of the conditional PDF given an event A that has positive probability. We know that the PDF is used to determine the probability of a small interval, and similarly, the conditional PDF is used to calculate the conditional probability of a small interval given the conditioning event. We would like to do something similar for the conditional PDF, where we would like to take the event A to be something like the event that y is equal to some particular value little y, but as we said, this is problematic because this event does not have positive probability. So instead, we can take A to be the event that y is approximately equal to a certain value. So we're dealing with a little interval around this value little y, which in general would be an event of positive probability, and we can try to have a similar interpretation. Let us see how this works out. So, what does it mean that y is approximately equal to some particular value little y? We interpret that as follows. We're told that the random variable y takes a value that is within epsilon, where epsilon is a small number, of a given value little y. And given this conditioning information, we want to calculate the probability of a small interval. How do we do that? Well, here, because this in general will be a positive probability event, we can use the definition of conditional probabilities, and it would be equal to the probability of both events happening. divided by the probability of the conditioning event. What is the probability of both events happening? This is a probability of a small rectangle in XY space. At that rectangle, the joint PDF has a certain value, and because we're integrating over that rectangle and that rectangle has dimensions delta and epsilon, that probability of that small rectangle is approximately equal to this. Then we need the denominator, which is the probability of the conditional event, and this is approximately equal to the density of y evaluated at that point times the length of the small interval. We cancel the epsilons, and then we notice that the ratio we have here is what we defined as the conditional PDF. So we get this relation times delta. So what do we see? We see that the probability of a small interval is equal to a PDF times the length of the small interval. However, because we are conditioning on y being approximately equal to a certain value, we end up using a corresponding conditional PDF, where the conditional PDF is defined this way. So we now have an interpretation of the conditional PDF in terms of probabilities of small intervals. Now that we have an intuitive interpretation of the conditional PDF, we can also use it to calculate conditional probabilities of more general events, not just intervals. And we do this as follows. In general, for continuous random variables, we can find the probability that x belongs to a certain set by integrating a PDF over that set. Because here we're dealing with a conditional situation where we're given the value of y, we use the conditional PDF instead of the true PDF, and this way we calculate a conditional probability. Now, the difficulty is that this conditional probability is not a well-defined quantity according to what we did early on in this class. We cannot condition on zero probability events, but we can get around this difficulty as follows. This quantity is well-defined, and we can use this quantity as the definition of this conditional probability. And so we have managed to provide a definition of conditional probabilities given a zero probability event of a certain type. It turns out that this definition is sound and consistent with everything else that we are doing. But when we're dealing with particular problems and applications, we can generally forget about all these subtleties that we have been discussing here. The bottom line is that we will be treating conditional PDFs, given the value of a random variable y, just as ordinary PDFs, but given the information that this random variable took on a specific value. And in that conditional universe, we will calculate probabilities the usual way by using conditional PDFs instead of ordinary PDFs. The definition of the conditional PDF is very simple. It is just this formula, which is analogous to the one for the discrete case. In all respects, mathematical and intuitive, it is very similar to the conditional PMF. Even so, developing a solid grasp of this concept does take some further thinking, so we will now make some observations that should be helpful in this respect. A first and obvious observation is that the conditional PDF is non-negative. It's defined when the denominator is positive, the numerator is a non-negative quantity, so it's always a non-negative quantity. A more interesting observation is that for any given value of little y, the conditional PDF looks like a slice of the joint PDF. Indeed, if you fix the value of little y, then the denominator in this definition is a constant, and we have a function that varies with x the same way that the joint PDF varies with x. Pictorially, let us consider this particular joint PDF, and let this be the x-axis, and let that be the y-axis. If we fix a certain value of y, if we condition on y having taken this particular value, so that our universe is now this particular line, on that universe, the value of the denominator in this definition is a constant, and the conditional PDF is going to vary according to the height of the joint on that particular conditional universe. So the height of the joint, if we trace it, is one of those curves up here, and it kind of goes down. So it is really a slice taken out of the joint PDF. If we condition on a different y, we get a different slice of the joint PDF, and so on. Actually, the conditional is not exactly the same as the slice. We also have this term on the denominator that serves as a scaling factor. It turns out that this scaling factor is exactly what we need for the conditional PDF given a specific value of little y to integrate to 1. Indeed, if we fix little y and take the integral over all x's, using the definition, and because this term is a constant and does not involve x, we only need to integrate the numerator, and we recognize that the numerator corresponds to our earlier formula for the marginal distribution, the marginal PDF of y. From the joint, this is how we recover the marginal PDF of y. So the numerator turns out to be the same as the denominator, and so we get a ratio of 1. Therefore, the conditional PDF for a given value of the random variable y behaves in all respects like an ordinary PDF. It is non-negative and it integrates to 1. The last observation is that we can take this definition and move the denominator to the other side to obtain this formula, which has the familiar form of the multiplication rule. The probability of two events happening is the probability of the first times the probability of the second given the first, except that here we're not really dealing with probabilities, we're dealing with densities. By symmetry, a similar formula must also be true when we interchange the roles of x and y. So, algebraically, everything is similar to what we have seen for the case of discrete random variables. It's the same form of the multiplication rule, although the interpretation is a bit different because densities are not probabilities. Conditional PDFs share most of the properties of conditional PMFs. All facts for the discrete case have continuous analogues. The intuition is more or less the same, although it is much easier to grasp in the discrete case. For example, we have seen this version of the total probability theorem. There is a continuous analog in which we replace sums by integrals and we replace PMFs by PDFs. The proof of this fact is actually pretty simple. By the multiplication rule, the integrand here is just the joint PDF of x and y. And we know that if we take the joint PDF and integrate with respect to one variable, then we recover the PDF, the marginal PDF of the other random variable. So this is one theorem that extends to the continuous case. Moving along, we have defined the conditional expectation in this manner in the discrete case, and we define it similarly for the continuous case. So actually here we now have a new definition. This definition is also consistent with the definition of the expectation of a continuous random variable. The expected value of a continuous random variable is the integral of x times a density, except that here we live in a conditional universe where we're conditioning on this event, and therefore we need to use the corresponding conditional PDF. Finally, we have the total expectation theorem. in the discrete case, and there is the obvious analog in the continuous case where we are using an integral and a density. The interpretation is that we consider all possibilities for y. Under each possibility of y, we find the expected value of x, and then we weigh those different possibilities according to the corresponding values of the density. So we're taking a weighted average of these conditional expectations to obtain the overall expectation of the random variable x. The derivation of this fact is maybe a little instructive because it uses various facts that we have in our hands. So let's see how to derive it. We start from this expression in the right-hand side, and we will show that it is equal to the expected value of x. The expression on the right-hand side is equal to the following. It's the integral of the density of y. And then inside here we have the conditional expectation, which is defined this way. So we just plug in the definition. And then what we do is we take this term and move it inside the integral, which we can do because this integral is with respect to x, and therefore this is like a constant. And we also interchange the order of integration. Now, the inner integration is with respect to y. As far as y is concerned, this term x is a constant, so we can take it and move it outside this first integral and place it out there. So this term disappears and goes out there. What do we have here? This part, by the previous fact, the total probability theorem, is just the density of x. So we're left with the integral of x times the density of x dx, and this is the expected value of x. Finally, we have various forms of the expected value rule which barely deserve writing down because they're exactly what you might expect. Consider, for example, an expression such as this one, the expected value of a function of the random variable x, but conditioned on the value of the random variable y. How do we calculate this quantity? Well, the expected value rule tells us that we should integrate g of x times the density of x. But because here we live in a conditional universe, we should actually use the corresponding conditional PDF of x. And there are many other versions of the expected value rule. Any version that we have seen for the discrete case has also a continuous analog, which looks about the same, except that we integrate and that we use densities. Independence is one of the central concepts of probability theory because it allows us to build large models from simpler ones. How should we define independence in the continuous case? Our guide comes from the discrete definition. By analogy with the discrete case, we will say that two jointly continuous random variables are independent if the joint PDF is equal to the product of the marginal PDFs. We can now compare with the multiplication rule, which is always true as long as the density of y is positive. So this is always true. In the case of independence, this is true. So in the case of independence, we must have that this term is equal to that term, at least whenever this quantity, the marginal of y, is positive. So, to restate it, independence is equivalent to having the conditional given y be the same as the unconditional PDF of x, and this has to be true whenever y has a positive density, so that this quantity is well defined, and it also has to be true for all x's. Now, what does this really mean? The conditional PDF, as we have discussed, in terms of pictures is a slice of the joint PDF. Therefore, independence is the same as requiring that all of the slices of the joint have the same shape, and it is the shape of the marginal PDF. For a more intuitive interpretation, no matter what value of y you observe, the distribution of x does not change. In this sense, y does not convey any information about x. Notice also that this definition is symmetric as far as x and y are concerned. So, by symmetry, when we have independence, it also means that x does not convey any information about y, and that the conditional density of y given x has to be the same as the unconditional density of y. We can also define independence of multiple random variables. The definition is the obvious one. The joint PDF of all the random variables involved must be equal to the product of the marginal PDFs. Intuitively, what that means is that knowing the values of some of the random variables does not affect our beliefs about the remaining random variables. Finally, let us note some consequences of independence, which are identical to the corresponding properties that we had in the discrete case, and the proofs are also exactly the same. So, the expectation of the product of independent random variables is the product of the expectations. The variance of the sum of independent random variables is the sum of the variances. And functions of independent random variables are also independent, which in particular implies, using the previous rule, that the expected value of a product of this kind is going to be the product of these expectations. So, independence of continuous random variables is pretty much the same as independence of discrete random variables as far as mathematics are concerned, and the intuitive content of the independence assumption is the same as in the discrete case. One random variable does not provide any information about the other. We will now go through an example that brings together all of the concepts that we have introduced. We have a stick of length L, and we break that stick at some random location, which corresponds to a random variable, capital X. And we assume that this random variable is uniform over the length of the stick, so its PDF has this particular shape. And for the PDF to integrate to 1, the height of this PDF must be equal to 1 over L. Then we take the piece of the stick that we are left with, which has length x, and we break it at a random location, which we call y, and we assume that this location y is uniformly distributed over the length of the stick that we were left with. What does this assumption mean? It means that if the first break was at some particular value little x, then the random variable y has a conditional distribution which is uniform over the interval from 0 to x. So the conditional PDF is uniform. A conditional PDF, like any other PDF, must integrate to 1, so the height of this conditional PDF is equal to 1 over x. Are x and y independent? No. One way to see it is that if you change little x, the conditional PDF of y would have been something different. Whereas, if we have independence, all the conditional PDFs have to be the same when you change the value of little x. Another way to see it is that if I tell you that x is 0.5, this gives you lots of information about y. It tells you that y has to be less than or equal to 0.5. So the value of the random variable x gives you plenty of information about the other random variable, and so we do not have independence. Notice that in this example, instead of starting with a full description of the random variables in terms of a joint PDF, we use a marginal PDF and then a conditional PDF to construct our model. Of course, with these two pieces of information, we can reconstruct the joint PDF using the multiplication rule. The marginal is 1 over L, the conditional is 1 over x, so the joint is equal to 1 over Lx. But for which values of x and y is this the correct expression? It is correct only for those values that are possible, So 0 has to be less than y, less than x, less than L. This is the range of values that are possible in this particular experiment, and we can visualize those values. They are those that correspond to this shaded triangle here. X and y are less than or equal to L, and y has to be less than or equal to x. If you try to visualize the joint PDF, notice that since it only depends on x, not on y, if you fix a value of x and you look at the slice of the joint PDF, the value of the joint PDF is going to be a constant on that slice. On this slice, it's going to be another constant, actually a bigger one. On that slice, an even bigger constant. And actually, this constant is bigger and bigger and goes to infinity as we approach 0. Of course, the fact that the slice is constant is just a reflection of the fact that the conditional PDF is constant over the range of values that a random variable can take. Let us now continue with some calculations. Let us find the marginal PDF of y. How do we do it? Since we have in our hands the joint PDF, we can find the marginal by integrating the joint. And in our case, the joint is equal to 1 over Lx, and we integrate over all x's. Now, what is the range of the integration? If we fix a certain value of y, the joint PDF is actually 0 in this region and in that region, so we should only integrate over x's that correspond to this interval. What is that interval? It's the interval that ends at L, and because this is a line of slope 1, this value here is also y. So we integrate over an interval where x ranges from y to L. In fact, this is just the range of x's that are possible for a given value of y. X must always be larger than or equal to y. Now, the integral of 1 over x is a logarithm, and using this fact, we can evaluate this integral, and it's 1 over L times the logarithm of L over y. For what y's is this a correct expression? Well, it makes sense only for those y's that are possible in this experiment, and that's the range from 0 to L. When y is equal to L, we have the logarithm of 1, which is equal to 0, so the value of the PDF is 0 here. As y decreases, this ratio increases and goes to infinity, so the log of that also blows up to infinity, and we get a shape of this form where the function that we're dealing with goes to infinity as we approach 0. Is this a problem, having a PDF that blows up to infinity? Not really. As long as the area under this PDF is equal to 1, it's still a legitimate PDF, and blowing up to infinity is not an issue. Let us now calculate the expected value of y. One way of doing this is by using the definition of the expectation. It's the integral of y times the density of y, which is 1 over L times the log of L over y. And the range of the integration has to be those values for which we have a non-zero density. So we integrate from 0 to L, which are the possible values of the random variable y. This is an integral that's pretty messy. One can actually integrate it using integration by parts, but the calculation is a bit tedious. So let us look for an alternative and more clever approach. The idea is to divide and conquer. We're going to use the total expectation theorem, where we're going to condition on x. The total expectation theorem tells us that the expected value of y is the integral over all possible values of the random variable x, which is from 0 to L, the density of x, which is 1 over L, times the conditional expectation of y given that x is equal to some little x. And we integrate over all x's. Why is this simpler? When we condition on x taking a specific value, y has a uniform distribution between 0 and x, and therefore this conditional expectation is the expectation of a uniform, which is 1/2 the range of that uniform. So we obtain the integral from 0 to L, 1 over L times x over 2 dx. And finally, that's an integral that we can evaluate easily, or we can think even in a simpler way. This expression here is the density of x. This is x itself, so the integral of this times x gives us the expected value of x. And there's only a factor of 1/2 that's left out there, so we obtain 1/2 the expected value of x. But now x itself is uniform on an interval that has length L, and therefore the expected value of x is L over 2, and so we get a final answer, which is 1/2 times L over 2, which is L over 4. This answer makes intuitive sense. If we break a stick once, the expected value of what we're left with is half of what we started with. But if we break it once more, then we expect it on the average to be cut by a factor again of 1/2, and so we expect to be left with a stick that has length 1/4 of what we started with. So this example is a particularly nice one because we used all of the concepts that we have introduced: marginal PDFs, joint PDFs, conditional PDFs, and the relations between them, as well as expectations, calculations of expectations, and conditional expectations, as well as the total probability theorem. Just in order to get some more familiarity with joint PDFs, let us look at independent normals. Actually, this is an important example because noise is often modeled by normal random variables, and noise terms that show up at different parts of a system or at different times are often assumed to be independent. Suppose that we have two standard normal random variables x and y with zero means and unit variances. If they're independent, their joint PDF is the product of the marginal PDFs and takes this form. This is just the PDF of a standard normal x and the PDF of a standard normal y, and we multiply them. If we are to plot this joint PDF, we obtain this figure. It looks like a bell, which is centered at the origin at the point with coordinates 0, 0. One way to think about what is going on here is to rewrite this expression as 1 over 2 pi and then the exponential of minus 1/2 x squared plus y squared. If we look at the unit circle in xy space, which is the set of points at which x squared plus y squared is equal to 1, then on that circle the PDF takes a constant value because this quantity is constant on that circle. And the same is true for any other circle. On any circle, the PDF takes a constant value, of course, a different constant. So the circles centered at the origin are the so-called contours of the joint PDF. On each contour, the joint PDF is a constant. Let us now generalize. Consider two independent normal random variables, but with general means mu x and mu y, and variances sigma x squared and sigma y squared. The joint is again the product of the marginal PDFs and therefore takes this form. This looks intimidating, but in fact it is pretty simple. This part is just a normalizing constant. It's the constant that's needed so that the joint PDF integrates to 1. What we have here is the negative exponential of a quadratic function of x and y. Let us plot the contours of this quadratic. Remember that a contour is the set of points where the quadratic takes a constant value, and by consequence the joint PDF also takes a constant value. If you set this quadratic to a constant, what you have is the equation that describes an ellipse, and it is an ellipse whose principal axes run along the x and y directions, and those ellipses are all centered at this particular point, mu x, mu y. The joint PDF is largest when the exponent is equal to 0. And this happens when x is equal to mu x and y is equal to mu y. That is right at the center of the ellipse. That's where the joint PDF is largest. As you move to ellipses that are further out on this outer ellipse, this expression is a constant. It's the exponential of the negative of some positive numbers, so you get a smaller value for the joint PDF. If you move to a further ellipse further out, then again the joint PDF will be a constant, but it's going to be a smaller constant. Now, for the case of standard normals, the joint PDF was circularly symmetric. The contours were actually circles instead of ellipses. But this is not the case in general. For example, suppose that the variance of y is bigger than the variance of x. Then you get a shape as the one shown in this figure. Since the variance of y is larger, we expect y to take values over a bigger range and to be larger typically than the values of x. And so the bell shape that we have for the joint PDF is stretched in the y direction. It extends further out in the y direction than it does in the x direction. To conclude, the joint PDF of two independent normals has the shape of a bell. The center of the bell is determined by the means. Furthermore, the bell is stretched in the x and y directions by an amount that is determined by the variances of x and y. However, the stretching is always along the coordinate axis. If you wanted a bell that stretches in some diagonal direction, or if you have contours that are ellipses but with some different kinds of axes, then you will have dependence between the two random variables. In that case, we will be dealing with a so-called bivariate normal distribution, but we will not pursue this any further at this point. If you remember our discussion from a long time ago, we said that much of this class consists of variations of a few basic skills and ideas, one of which is the Bayes rule, the foundation of inference. So let us look here at the Bayes rule again and its different incarnations. In a discrete setting, we have a random variable with a known PMF, but whose values are not observed. Instead, we observe the value of another random variable, call it y, which has some relation with x. And we will use the value of y to make some inferences about x. The relation between the two random variables is captured by specifying the conditional PMF of y given any value of x. Think of x as an unknown state of the world and of y as a noisy observation of x. The conditional PMF tells us the distribution of y under each possible state of the world. Once we observe the value of y, we obtain some information about x, and we use this information to make inferences about the likely values of x. Mathematically, instead of relying on the prior for x, we form some revised beliefs, that is, we form the conditional PDF of x given the particular observation that we have seen. All this becomes possible because of the Bayes rule. We have seen the Bayes rule for events, but it is easy to translate into PMF notation. We take the multiplication rule and we use it twice in different orders to get two different forms or two different expressions for the joint PMF. We then take one of the terms involved here and send it to the other side. We obtain this expression, which is the Bayes rule. What do we have here? We want to calculate the conditional distribution of x, which we typically call the posterior. And to do this, we rely on the prior of x as well as on the model that we have for the observations. The denominator requires us to compute the marginal of y. But this is something that is easily done because we have the joint available. The numerator, this expression here, is just the joint PMF, and using the joint PMF, you can always find the marginal PMF. Essentially, we're using here the total probability theorem, and we're using the pieces of information that were given to us, the prior and the model of the observations. When we're dealing with continuous random variables, the story is identical. We still have two versions of the multiplication rule. By sending one term, this term, to the other side of the equation, we get the Bayes rule. And then we use the total probability theorem to calculate the denominator term. So, as far as mathematics go, the story is pretty simple and is exactly the same in the discrete and the continuous case. This story will be our stepping stone for dealing with more complex models, and also when we go into more detail on the subject of inference later in this course. We have seen two versions of the Bayes rule, one involving two discrete random variables and another that involves two continuous random variables. But there are many situations in real life when one has to deal simultaneously with discrete and continuous random variables. For example, you may want to recover a discrete digital signal that was sent to you, but the signal has been corrupted by continuous noise, so that your observation is a continuous random variable. So suppose that we have a discrete random variable k and another continuous random variable y. In order to get a variant of the Bayes rule that applies to this situation, we will proceed as in the more standard cases. We will use the multiplication rule twice to get two alternative expressions for the probability of two events happening. We will equate those expressions and from these derive a version of the Bayes rule. So we will look at the probability that the discrete random variable takes on a certain numerical value, and simultaneously the continuous random variable takes a value inside a certain small interval. So here delta is a positive number, which we will take to be very small, and in fact we will be interested in the limiting case as delta goes to 0. So now we use the multiplication rule. The probability of two events is equal to the probability of the first event times the conditional probability of the second event, given that the first event has occurred. But we know that we can use the multiplication rule in any order, so the probability of two events happening can also be written as the probability that the second event occurs times the conditional probability that the first event occurs, given that the second event has occurred. So these two expressions that we obtain from the multiplication rule have to be equal. Let us rewrite those expressions using PMF notation and PDF notation. What do we have here? The probability that a discrete random variable takes on a certain value, that's just the PMF of this random variable evaluated at a particular point. And what do we have here? The probability that a random variable, y, a continuous random variable, takes values inside an interval is always equal to the PDF of that random variable times the length of this interval. And this is an approximate equality. However, because here we're talking about the probability of being in a small interval conditioned on a certain event, we should be using a conditional PDF. It's the conditional PDF conditioned on the random variable capital K and conditioned on the specific event that this discrete random variable takes on a certain value little k. Let us do a similar notation change for the second expression. Here we have the probability, the unconditional probability that y takes a value inside the small interval, and when delta is small, this is approximately equal to the PDF of the random variable y times the length of the interval. And what do we have here? The probability that a discrete random variable takes on a certain value that just corresponds to the PMF of that random variable. However, we're talking about a conditional probability given that a random variable y takes a value that's approximately equal to a certain little y. So this is a notation that we have not used before, but its meaning should be unambiguous at this point, but just by arguing by analogy to what we have been doing all along. It's a PMF of a discrete random variable, but it is a conditional PMF. It describes us the probability distribution of the discrete random variable k when the random variable y, which happens to be a continuous one, takes on a specific value. So we can cancel the deltas from both sides, and we have that this expression is approximately equal to that expression, and this approximate equality is more and more exact as we send delta to 0. But delta has already disappeared from here, so we can set these two expressions equal to each other. At this point, now we can take this term and move it to the other side of the equality, so it will go to the denominator, and we obtain this version of the Bayes rule. It gives us the conditional probability of a random variable k given that a certain continuous random variable y has taken on a specific value. So this version is useful if we have a continuous noisy observation y on the basis of which we're trying to say something to make inferences about the discrete random variable k. And in order to apply the Bayes rule, we need to know the unconditional distribution of the random variable k, and we also need to have a model of the noisy observation, a model of that observation under each possible conditional universe. So for any possibility for the random variable k, we need to know the distribution of the random variable y. Or alternatively, we can take this term and send it to the denominator of the other side, and we get a different version of the Bayes rule. This version of the Bayes rule applies if we're trying to make an inference about a continuous random variable y, given that we know the value of a certain related observation k of a random variable capital K. In both versions of the Bayes rule, there is also a denominator term which needs to be evaluated. This term gets evaluated similar to the cases that we have considered earlier, and they are determined by using a suitable version of the total probability theorem. This is a version of the total probability theorem that we have already seen. We have a conditional density of y under different scenarios for the random variable capital K, and we get the density of y by considering the conditional densities and weighing them according to the probabilities of the different discrete scenarios. This version of the total probability theorem is something that we have not proved so far, and we have not seen it. On the other hand, it's not hard to derive. If we fix the value of k, this is a density, and therefore it must integrate to 1. So the integral of this ratio with respect to y has to be equal to 1. Now there's no y in the denominator, so the integral of the numerator divided by the denominator has to be equal to 1, which means that the denominator must be equal to the integral of the numerator when we integrate over all y's, and this is just what this expression is saying. So what we will do next will be to consider one example for each one of these two cases of the Bayes rule that we have just derived. We will now use the Bayes rule in an important application that involves a discrete unknown random variable and a continuous measurement. Our discrete unknown random variable will be one that takes the values plus or minus 1 with equal probability. And the measurement will be another random variable y, which is equal to the discrete random variable, but corrupted by additive noise that we denote by w. So what we get to observe is the sum of k and w. This is a common situation in digital communications. We're trying to send one bit of information, whether k is plus 1 or minus 1, but the observation that we're making is corrupted by a communication channel, by some noise that is present in the channel. And on the basis of the value of y that we will observe, we will try to guess what was sent. The assumption that we will make about the noise is that it is a standard normal random variable. So, suppose that we observed a specific value for the random variable y. We want to make a guess about the random variable capital K. Of course, there's no way to guess with complete certainty. The only thing that we can say is to determine how likely it is that a 1 was sent as opposed to how likely it is that a minus 1 was sent. How do we approach such a problem? Well, we use the version of the Bayes rule that we have already developed, and which is this formula that gives us the conditional probabilities that we want. And in particular here, we're asking a question about the conditional probability that k takes the value of 1, given that a value of y has been observed. This is what we want to calculate. So let us look at the various terms involved here and see what each term is. First, we need the prior probability of k. This is simple. The prior probabilities are 1/2 for k equal to minus 1 or plus 1, because we said that the two possibilities are equally likely. Then we need the conditional density of y given k. Okay, so what does this assumption mean? It means that y is a standard normal random variable to which we add the value of k. So if k is equal to 1, we're taking a standard normal and we add a value of plus 1. So y, given that k is equal to plus 1, is going to be a standard normal plus 1. What does that do? If we take a standard normal and add a constant to it, that changes the mean and makes the mean equal to 1 and does not change the variance. On the other hand, if k happens to be equal to minus 1, then the observation that we see is going to be a standard normal plus a value of minus 1, and that changes the mean to become minus 1, but with a variance of 1. So if we are to plot the density of y, that density, of course, will depend on what the value of k was. And if k is equal to 1, then we will obtain a normal that has a mean of 1, so it's centered here. But if k is equal to minus 1, then our observation will be a normal with unit variance, but centered at minus 1. So, if we are to write this in terms of symbols, the distribution of y is normal with variance equal to 1. So the PDF is given by this form: e to the minus 1/2 y minus the mean of y. But given the value of k, the mean of y is equal to k plus or minus 1, depending on what k is. So this is the PDF of a normal with unit variance and mean equal to k. And it corresponds, when you set k equal to 1, it corresponds to this graph. When you set k equal to minus 1, it corresponds to that graph. Let us continue with the next term in this expression. We need the term in the denominator, which is obtained by taking a sum over the different choices of k. There are two choices, and each choice has a probability of 1/2. From the first choice, we have 1/2 times the density of y when k is equal to -1. And when k is equal to -1, we obtain this expression. And we have another term that corresponds to the case where k is equal to +1, in which case we have this expression here. Once more, this expression here corresponds to this normal with a mean of -1. This expression here corresponds to a normal with a mean of +1, which is this graph here. So at this point, we have in our hands expressions for everything that is involved here, and we can just apply the formula and carry out a fair amount of algebra. There are some very nice simplifications that happen along the way, and we end up with an answer that has the following form. It's 1 divided by 1 plus e to the minus 2y. And this gives us the probability that the 1 was sent. Let us try to make sense of this expression. Let's see what it looks like by plotting it as a function of y. So what we're plotting here is this expression. Okay, if y is very large, as y goes to +infinity, this term disappears and we obtain a 1. If on the other hand y is very, very negative, so y goes to -infinity, here we get e to the infinity, which is a very large number, so this ratio is going to converge to 0. So we have a graph that starts at 0, it actually rises monotonically, and in the limit converges to 1. If y is equal to 0, then this term is 1, and we obtain a 1/2. Let us interpret this plot. If y is very large, it is much more likely that y is coming out of this distribution, so that k is equal to 1. So the probability that k is equal to 1, if we obtain this observation, is almost 1. We have almost certainty. If, on the other hand, y is very, very negative, then it is much more likely that what we're seeing is coming from this distribution, so that k is equal to -1. And in that case, the probability that k was 1 is going to be approximately 0. Finally, if y is 0, then we're just in the middle of the two possibilities, and by symmetry, either choice of k is equally likely. Therefore, the posterior probability that k is equal to 1, given that y was equal to 0, that probability is 1/2. When y is equal to 0, it's equally likely that either signal was sent. This example is a prototype of the kind of calculations that are done in the analysis of communication systems. This is the simplest model of communication of a single bit in the presence of additive noise, but of course there can also be more complicated models in which we have more complicated signals that are sent and more complicated models of the noise. But the general principles of the analysis are always of this kind. We are using the Bayes rule, and we need to write down the different terms that are involved. We now look at an application of the Bayes rule that involves a continuous unknown random variable, which we try to estimate based on a discrete measurement. Our model will be as follows. We observe a discrete random variable k, which is Bernoulli, so it can take two values, 1 or 0, and it takes those values with probabilities y and 1 minus y respectively. This is our model of k. The catch is that the value of y is not known, and it is modeled as a random variable by itself. You can think of a situation where we are dealing with a single coin flip. We observe the outcome of the coin flip, but the coin is biased. The probability of heads is some unknown number y, and we try to infer or say something about the bias of the coin on the basis of the observation that we have made. So what do we assume about this y, or the bias of the coin? If we know nothing about this random variable, we might as well model it as a uniform random variable on the unit interval. And the question now is, given that we made one observation and the outcome was 1, what can we say about the probability distribution of y given this particular information? So the question that we're asking is what we can tell about the density of y given that the value of 1 has been observed. The way to approach this problem is by using a version of the Bayes rule. We want to calculate this quantity for the special case where k is equal to 1. So let us calculate the various pieces on the right-hand side of this equation. The first piece is the density of y. This is the prior density before we obtain any measurement. And since the random variable is uniform, this is equal to 1 for y in the unit interval. And of course, it is 0 otherwise. The next piece that we need is the distribution of k given the value of y. Well, given y, k takes a value of 1 with probability equal to y. So the probability of 1, if we're told the value of y, is just y itself. Y is the bias of the coin that we're dealing with. The next term that we need is the denominator. We will use this formula. It is the integral of the density of y, which is equal to 1, and it is equal to 1 only on the range from 0 to 1, times this probability that k takes a value, a certain value. In this case, we're dealing with a value of 1, so here we're going to put a 1 instead of k. And therefore, we're dealing with this expression here, which is just y, and we integrate it over y's. So this is y squared over 2, evaluated at 0 and 1, which gives us 1/2. So this is the unconditional probability that k is equal to 1. If we know nothing about y, by symmetry, higher biases are equally likely as lower biases, so we should expect that it's equally likely to give us a 1 as it is to give us a 0. Now we have in our hands all the pieces that go into this particular formula, and we can go ahead with the final calculation. So in the numerator, we have 1 times this term, evaluated at k equal to 1, which is equal to y. And then in the denominator, we have a term that evaluates to 1/2. So the final answer is 2y. Over what range of y's is this correct? Well, only for those y's that are possible. So this is for y's in the unit interval. If we are to plot this PDF, it has this shape. This is a plot of the PDF of y given that the random variable k takes on the value of 1. Initially, we started with a uniform for y, so all values of y were equally likely. But once we observed an outcome of 1, this tells us that perhaps y is on the higher side, on the higher end rather than the lower end. So after we obtain our observation, the random variable y has this distribution with higher values being more likely than lower values. This example is a prototype of situations where we want to estimate a continuous random variable based on discrete measurements. Essentially, it is the same as trying to estimate the bias of a coin based on a single measurement of the result of a coin flip. As you can imagine, there are generalizations in which we observe multiple coin flips, and this is an example that we will see later on in this class.